Welcome back to another session with AD Tutoring. In this video, we're going to break down the mean value theorem and show you how much sense it actually makes, and how if you know what the mean value theorem does, then you know what Rolle's theorem is as well. So let's get right to it. The mean value theorem states that if some function, and let's say f of x, is differentiable on the interval a to b, and this is an open interval, then there exists at least one value, and we're going to call that c, in that interval, such that f prime at c is equal to the quotient of f of b minus f of a all over b minus a. So what does this mean? Let's go ahead and break it down. If we're looking at that f prime of c, what does that mean? That means that this is the instantaneous rate of change of that function at c. Breaking down the right side of the equation, well, that's just a slope formula. That's just the average rate of change between A and B. So in English, if we were to compute the slope between two values on a differentiable function, then there is some point between those two whose instantaneous rate of change or derivative at that point is the same as the average rate of change between those two that we computed earlier. And so let's go ahead and solidify this with visuals. Let's take a look at this function's graph. I'm going to label this f of x, and it starts at A, ends at B. And so this function is continuous on the interval AB inclusive, and it's differentiable on A to B non-inclusive. The reason that this function is differentiable on A to B non-inclusive is because when we take the derivative, it's a limit. And so when we take the limit, we know we need two sides. And so if we're looking at A and B, we have nothing. We're not guaranteed anything prior to A, and we're not guaranteed anything after B. And so because the limit will need to be two-sided, we wouldn't have that reference to the left. We're not guaranteed that reference to the left, and we're not guaranteed that reference to the right in the mean value theorem. We're only guaranteeing A to B. So anything before and after, we can't guarantee. And so therefore, we can only say that it's differentiable on A to B non-inclusive. So just in case you were curious about that, that's why that is the way it is. So looking at this function, it's clearly differentiable. It's a smooth curve. We're all good. Let's take a look and see what happens if we were to connect A to B, because that would essentially show us the secant line from A to B. If we were to take the slope between A and B, we would have a slope, and this would be it. This line would represent that slope. What the mean value theorem essentially states is that if this function is differentiable, which it is, on A to B, there's the interval, all the mean value theorem states is that since it's differentiable, we're guaranteed to have some point on this curve from A to B, some point, its tangent line will have the same slope as this secant line. That is exactly and essentially what the mean value theorem states. One of these tangent lines, at least one of them, will have the same slope as this secant line from A to B. And let's go ahead and prove it. Let's put our money where our mouth is. Let's try to see if we can find out where it is. Here's the tangent line. Let's go ahead and start moving. So let's see. As we go, looks like we're going, and oh, guess what? Let's go ahead and go back a little bit. Looks like right around here. Look at that. That tangent line looks parallel to that secant line. And if you know anything about algebra, parallel lines have the same slope. So that's what I mean. So yeah, it looks like we found some point right here that has the same slope as that secant line. That's what the mean value theorem states. We're guaranteed to have one of those points. Let's see if we can find any more. We're guaranteed at least one, but let's see if on this particular one we have any more. And guess what? Sure enough, we do, right around there. Let's go ahead and go back just a little bit. Right here. It looks like if we're right about there, yeah, this is a parallel, these are parallel lines. And so then again, we found another point that will have the same slope as the secant line. Or to be more exact and direct, the derivative at this point is equal to f of b minus f of a all over b minus a, or the slope between those 2 points. And to go even further, let's go ahead and show you one more point. One more point. It looks like right around, ooh, I went way past, but right around there. Yeah, there we go. There's another one. We have another point where its tangent line's slope is the same as the slope of this secant line. And that's what the mean value theorem is. So again, if on a differentiable curve on an interval a to b, so let's say a function is differentiable on some interval a to b, if we were to take the slope from the endpoints, we can guarantee that we will find some point on the curve along the way that will have the same slope as the secant line. And again, to be more direct, we are guaranteed to find some point, I'm going to call it C, where the derivative of this function evaluated at C is equal to the average rate of change between A and B, or the endpoints of that interval. And that is it. Now let's go ahead and take a look at another example. This is some function f of x, and it's differentiable along the interval A to B. So taking a look at this, let's go ahead and connect those two endpoints, A and B, with a secant line. If we were to do so, we'll see that this looks like a horizontal line. Okay, cool. So it looks like a horizontal line, and so if we have a horizontal secant line or a horizontal tangent line, remember that means that the slope is 0. And since we're taking the slope between A and B, for the slope to be 0, this means that f at A and f at B need to be the same value. Because if they're the same value, we'll get a 0 in the numerator. The difference between A and B in the denominator, it could be A is 1, B is 3. That could be, 2, 0 over 2 is still 0. So that's what I'm getting at right there. What I'm getting at is that f at A and f at B have the same value. Okay, it's nothing special. That's just a horizontal tangent line, or horizontal secant line. Sorry about that. It's just a horizontal secant line. So let's go ahead and see if we can still apply the mean value theorem. And guess what? We still can. Looking at this secant line, or the tangent line, let's just go ahead and see what happens. Let me go and speed it up a little bit, because I think we know where that tangent line might be. And yeah, so while we approach it very slowly, remember, the slope of the tangent line, or the derivative at a certain point, needs to match the slope of the secant line. And guess what? Sure enough, it's there. Right around there. And there we go. Look at that. We found some point right there that has a tangent line that is also horizontal. That secant line is horizontal. That's all it is. The mean value theorem applies because this function is differentiable along the curve. And yeah, we're good. And this is called Rolle's theorem. Now, if I caught you by surprise, don't worry. Rolle's theorem is just an extension of the mean value theorem. That's all it is. It's just a very, very specific case of the mean value theorem. Like I said, the mean value theorem, if you were to take the slope between A and B, then there exists a value between A and B that has the derivative equal to that slope value. Rolle's theorem, it's the same as the mean value theorem, except the slope between A and B just so happens to be 0. It just so happens to form a horizontal secant line. And so what Rolle's theorem states, just like the mean value theorem, well, there must be some value along this curve that has a tangent line whose slope is equal to the slope of the secant line. And it just so happens that this case, it's horizontal. And so there exists some maximum or minimum, basically, is what Rolle's theorem is saying. There would exist a maximum or minimum that would give us the same slope, a slope of 0. And I hope this makes sense. I hope you weren't confused at first in school, because it can get a little confusing when you look at all these theorems because they keep piling on and piling on. But the mean value theorem and Rolle's theorem are theorems that should not give you much trouble at all after this video, hopefully. And let's not stop there. Let's go ahead and try to tackle some problems using our knowledge and applying it to algebra, using algebraic techniques. So suppose we were given f of x equals x squared. And we were asked if the mean value theorem applies for this function on the closed interval from 1 to 5. All right, well, step one, we got to ask ourselves, if the mean value theorem is going to apply, is this function differentiable along that interval? Well, let's see. So x squared, well, we know that that function is definitely differentiable along any interval. So yes, it would be differentiable along 1, 5. And the reason that this is a closed interval, this is because it's defining its continuity. So don't be confused when you see that in your textbook. It really shouldn't be a big deal anyway. It really isn't. But just want to make sure that you know that. So from 1 to 5, that's its continuity. If we're looking at its differentiability, we're talking the open interval 1, 5. But just want to make sure that that's known, very clear. It's really not that big of a deal, but you need to know that. So, yep, x squared is definitely differentiable. So next, we got to find out, okay, what value is it that applies? Well, first, we got to go ahead and find the slope between 1 and 5. So let's go ahead and take that, because we're guaranteed that f prime at some value, let's call it c, is equal to the slope between those 2 points. So f at 5 minus f at 1. All I'm doing is taking the slope formula. All I'm doing is performing the slope. So here, f at 5 minus f at 1. So this means that f prime of c equals, so f at 5. So 5 squared, that's 25. Minus 1 squared, or minus 1. All over 5 minus 1, which is 4. This is equivalent to 25 minus 1. That's 24. Divided by 4. This equals 6. This equals 6. So therefore, we are looking for some value or some x value on the derivative that has a value of 6. Or we're looking for a value c for which the slope of its tangent line is 6. They both mean the same thing. They both mean the same thing. So this is what we're looking for. This is what we're looking for. The c for which this holds true. Well, to figure it out, well, first we need to take the derivative. So let's go ahead and perform the derivative. We should know by now the derivative of x squared is 2x. All right, step 1, complete. Take the derivative. Up next, let's go ahead and set that derivative equal to 6. Because f prime at c, we can replace that f prime of c, or not f prime of c, we can replace the f prime with 2x, and we want to set it equal to 6. And we're going to find that c value. Well, I think we're pretty much done here already. All we got to do is divide both sides by 2, and then we'll have x equals 3. And there we go. That's that c value. The c value is 3. It is 3. So at x equals 3, or the better way we can say it is, x equals 3 is the x value which satisfies the mean value theorem for this problem. And like always, we can go ahead and support this with the graph. Take a look at that graph. I only graphed from 1 to 5. And then look at that secant line and look at that tangent line at x equals 3. They are parallel. The mean value theorem holds true. Up next, let's go ahead and tackle some Rolle's theorem. Let's go ahead and say that we were given a function f of x equals x squared minus 4x plus 1. And we were asked if Rolle's theorem applies on the interval 0 to 4. So on the closed interval 0 to 4, does Rolle's theorem apply? Rolle's theorem, like I said before, it's essentially the same thing as the mean value theorem, except we would see that the slope between these 2 points should be 0. That's it. So let's see if Rolle's theorem applies. This is a parabola, a parabolic function, x squared minus 4x plus 1. We know that if we were to take the derivative, it would be continuous. So this function is differentiable. Check 1. Up next, let's go ahead and take the slope between 0 and 4. If we were to compute that, we would have f at 4 minus f at 0 all over 4 minus 0. This slope will be, should be, so we have a 4 in the denominator. F at 4, well, let's go ahead and expand this just for our viewers who might need to see this. So 4 squared, that's 16, minus 4 times 4, so that's going to be minus 16, plus 1. And then we're going to subtract f at 0. So minus, well, 0 squared is 0, minus 4 times 0, that's 0, plus 1. So that's 1. So we'll subtract it. So we have 16 minus 16, eliminate those, plus 1 minus 1, those eliminate as well. And so we're left with 0 over 4, which is equal to 0. So yes, Rolle's theorem does apply, because the slope between the 2 endpoints of the interval is 0. So what we need to do next is we need to find some c value where the derivative evaluated at that value is also equal to 0, where the instantaneous rate of change of this function at some value between 0 and 4 is 0. So what do? Well, first off, we take the derivative of this function. So the derivative of f of x will be f prime of x equals the derivative of x squared, that's 2x, minus 4x, so that'll turn into minus 4, plus 1, derivative of any constant is 0. So our derivative is equal to f prime of x is 2x minus 4. Well, since we're looking for where this function, the derivative, equals 0, that's all we got to do. Take 2x minus 4, set it equal to 0, then solve for x. In doing so, we'll add 4 to both sides, which will leave us with 2x equals positive 4. And then lastly, we divide both sides by 2 to receive x equals 2. And there we go. We have solved for that c value. So the value for which that satisfies the Rolle's theorem for this particular situation is x equals 2. Let's go ahead and take a look at the graph. And there it is. From 0 to 4, we see that we have a horizontal secant line, which means that the slope of that secant line is 0. And if we take a look at x equals 2, that tangent line also has a slope of 0. So yes, Rolle's theorem holds true, and we can confirm it always with a graph. And that's it. That's pretty much it for the mean value theorem and Rolle's theorem. For a quick recap, they are both one and the same. Mean value theorem and Rolle's theorem are the same. The only difference is that Rolle's theorem is just a very specific case where when you take the slope between those 2 points, it just so happens to be 0. And for some reason, we decided to give it the name Rolle's theorem for that. Essentially, they're the same thing. I could call any Rolle's theorem problem a mean value theorem problem because that's actually correct. But for the most part, here's a general guideline for the mean value theorem and Rolle's theorem. First, make sure that your function, your given function, is differentiable along the interval for which you're given. Next, compute the slope between the 2 points on the interval. If the slope happens to be 0, then Rolle's theorem applies. If it so happens to be something else, then that's just the mean value theorem. But either way, even if it's 0, the mean value theorem would still apply. Just watch out and state Rolle's theorem just in case your professor or instructor wants you to state that Rolle's theorem actually applies. Nevertheless, once you compute the slope between the interval, we want to go ahead and take the derivative of the function and find that value on that interval for which the slope of the tangent line or the derivative is equal to that slope that we calculated. And that's it. That is the mean value theorem and Rolle's theorem. It's quite simple, and it should be. So go ahead and practice it. Let me know if you'd like any help. I'll be more than happy to. And then watch the next video where I'll go ahead and be tackling indeterminate limits one more time. And we're going to be using this method called L'Hopital's rule. And that's going to help us tackling indeterminate limits way back when we were talking about limits and continuity. And I'm going to show you how it can actually be very, very, very easy with this rule. So until next time, guys, have fun. I hope this video helped.